China and Russia just announced they're building a nuclear power plant on the moon by 2035. Not a research experiment, a full-scale automated facility to dominate the lunar surface with permanent human presence. America's response? Beat them there by 2030 with a technology so efficient it makes solar panels look primitive. But here's what nobody's talking about. Why is Elon Musk betting everything on this nuclear solution when solar already powers the ISS? What makes this approach so genius that it could decide who controls space for the next century? The answer starts with understanding the moon's brutal reality. Picture this. One lunar day equals 2 full Earth weeks of blazing sunlight, followed by 2 weeks of pitch-black darkness, where temperatures plummet to -200 degrees Fahrenheit. Solar panels? They become useless metal sheets the moment the sun disappears. Batteries lose efficiency in that bone-chilling cold. Meanwhile, a fission reactor keeps humming for over a decade straight, no matter what the moon throws at it. So here's the real question. If solar can't survive 14 days of darkness, how could we ever build anything permanent up there? The logistics tell an even more compelling story. NASA's lunar reactor needs just a few kilograms of enriched uranium-235 to run for years. That's a tiny package in a Starship that can haul 100 tons. Compare that to solar power for the same output. You'd need kilometers of panel arrays, thousands of battery packs, and dozens of Starship missions just to transport everything. The math isn't even close. But this creates an interesting engineering debate that's been raging behind closed doors. Some engineers pitched an audacious idea. Why not convert entire starships into modular nuclear reactors? Land them, plug them in, instant power. Need more energy as the base grows? Send more starships. On paper, it sounds brilliant. But when you break down the physics, the concept falls apart fast. A starship stands 50 meters tall when fueled, weighs 100 to 150 tons empty, and measures 9 meters wide. NASA's 100-kilowatt reactor, under 6 tons total, fits in a compact cargo bay. Converting a starship wastes more than 90% of its mass on empty structure instead of actual power generation. That's like buying a mansion to store a microwave. Then there's the radiation problem nobody wants to discuss publicly. Starship's thin stainless steel hull can't contain nuclear radiation any better than aluminum foil stops bullets. You'd need tons of lead shielding or water barriers. The cooling systems alone would require massive radiators extending beyond the ship. Power cables would stretch across the lunar surface, exposed to micrometeorite impacts and temperature swings of 500 degrees between day and night. Every connection point becomes a potential failure that could shut down the entire base. And here's what makes this even more problematic. Lunar dust. That fine, abrasive regolith gets into everything. It's not like beach sand. It's sharp, electrostatically charged, and sticks to surfaces like glue. During Apollo missions, it damaged spacesuits, clogged seals, and scratched visors after just a few days. Running a nuclear reactor inside a starship means that dust infiltrates cooling systems, degrades seals, and creates maintenance nightmares that could turn catastrophic. How do you repair a radioactive cooling system when your technicians can only work in bulky spacesuits for limited hours? NASA's approach cuts through all this complexity with elegant simplicity. Their reactors are compact, portable, and designed to be buried underground where lunar soil provides natural radiation shielding. When a mission lands, crews deploy the unit in hours, not weeks. The Kilopower project proved this concept works beautifully. Tested in 2018, these systems use uranium fuel and heat pipes with 0 moving parts. They run silently for a decade, producing 1 to 10 kilowatts, scalable to 40 kilowatts for Artemis missions by 2030 through partnerships with Lockheed Martin and Westinghouse. Each reactor weighs between 1 and 6 tons, launches safely in a cold, inactive state, and generates enough electricity to power 70 to 100 homes continuously through those brutal lunar nights. But what about China and Russia's mysterious project? The global space community has been buzzing with theories because calling it a nuclear power plant seems technically impossible on the moon. Conventional reactors need massive water volumes for cooling and steam generation. Transporting tons of water from Earth would cost billions. However, there's a clever counterargument gaining traction among planetary scientists. What if they're planning to harvest lunar ice from the South Pole? Recent data confirms substantial water ice deposits in permanently shadowed craters. If that ice can be extracted and processed, it could solve the cooling problem without Earth resupply missions. But does this actually work, or is it wishful thinking that ignores engineering reality? The heat dissipation challenge reveals the deeper problem. Large reactors generate intense waste heat that must be radiated into space. On Earth, you dump heat into oceans, rivers, or the atmosphere. The moon has none of that. Radiators would need to be enormous to shed heat through thermal radiation, alone in a vacuum. Balancing between overheating and overcooling in the harsh lunar environment requires complex engineering that makes Earth-based nuclear plants look simple. This is why several experts believe the power plant terminology is misleading propaganda designed to sound impressive for political purposes. The most probable explanation: they're actually referring to radioisotope thermoelectric generators, RTGs, or what the industry calls nuclear batteries. These aren't flashy. They produce only about 20 watts each, roughly enough to power an LED bulb. But here's their superpower. They run continuously for decades without moving parts, maintenance, or caring whether it's day or night. RTGs have powered Voyager probes for over 45 years, still transmitting data from beyond our solar system. They kept Curiosity and Perseverance rovers exploring Mars through dust storms that would kill solar panels. For early lunar operations where reliability trumps raw power output, RTGs make perfect strategic sense. The United States isn't new to this game. NASA launched its first RTG in 1961 and has deployed them on countless deep space missions since. Russia, even more aggressive. During the Soviet era, they built thousands of RTGs and launched satellites equipped with actual nuclear reactors like the Topaz system, 310 kilograms producing 5 kilowatts of power. That's impressive engineering from the 1980s. But growing evidence suggests China and Russia might be developing something more sophisticated this time around. Enter helium-cooled reactors, specifically high-temperature gas reactors, or HTGRS. China already operates a commercial version called the HTRPM, which uses helium gas instead of water as coolant. This design achieves high efficiency and inherent safety while completely avoiding water transport and freezing issues on the moon. Other advanced concepts use molten materials, salt, lead, or sodium, as coolants. These substances handle extreme heat without pressurized water systems. NASA's own crusty reactor demonstrated that compact fission systems operate safely in vacuum environments using liquid metal heat pipes. Russia brings decades of experience with sodium-potassium-cooled systems like the BES-5 reactor, plus ongoing research into molten salt and molten lead technologies. These designs are efficient, compact, and genuinely suited for space applications. So the realistic future of lunar nuclear power splits into two categories: RTGs for long-lasting, low-power applications that need bulletproof reliability, and advanced fission reactors using gas or liquid metal cooling for high power demands. Traditional water-cooled reactors? They belong on Earth where water is abundant and gravity helps everything. But nuclear power does something even more game-changing than keeping lunar bases alive. It's the key to reaching Mars in half the time. On the Moon, reactors keep the lights on. In space, that same heat becomes propulsion. Nuclear thermal rockets superheat hydrogen propellant in a reactor core and blast it out through a nozzle for thrust. The result? Double the efficiency of chemical rockets. A Mars trip that takes 6 to 9 months with conventional engines drops to just 3 or 4 months. Less time means lower radiation exposure for crews and significantly reduced psychological stress from confinement. After decades of research and false starts, nuclear propulsion technology is finally reaching a genuine turning point where deployment becomes viable within 5 years if funding continues. Two systems are racing toward reality. Nuclear thermal propulsion uses a compact reactor to heat liquid hydrogen and expel it for thrust. NTP engines deliver strong thrust similar to chemical rockets, but with much better fuel efficiency. You get twice as much velocity change from the same fuel mass. Then there's nuclear electric propulsion, which converts reactor heat into electricity powering ion thrusters. NEPI produces less thrust, but runs far more efficiently, perfect for cargo missions where you have months to accelerate gradually. For crewed missions demanding faster transit, NTP wins. For heavy cargo where time matters less than efficiency, NEP dominates. To prove NTP works in the real environment of space, NASA and DARPA partnered on the Draco program, demonstration rocket for agile cislunar operations. This isn't a paper study. It's an actual nuclear thermal rocket engine that will be tested in orbit, marking humanity's first nuclear propulsion demonstration in space since the 1970s. Draco proves the technology is safe, reliable, and ready for deep space missions. Why does this matter so urgently? Because the nation that masters nuclear space propulsion doesn't just reach Mars faster. They control the entire economic future of the solar system, from asteroid mining to establishing permanent settlements across multiple worlds. This isn't just about beating China to the moon by 5 years. It's about who writes the rules for the next 1,000 years of human civilization. Nuclear power on the moon determines which nation establishes the first permanent extraterrestrial economy. Nuclear propulsion decides who reaches Mars first, who mines asteroids for trillions in resources, and ultimately who becomes the spacefaring civilization that survives beyond Earth. Elon Musk understands this at a level most people miss. SpaceX's Starship isn't just a rocket, it's the delivery system for humanity's nuclear future in space. Every reactor NASA deploys, every nuclear thermal engine DARPA tests, every kilowatt generated on the lunar surface shifts the balance of power away from nations stuck thinking in terms of solar panels and chemical rockets. The genius of this approach isn't the technology itself. It's recognizing that whoever controls energy in space controls everything that follows. China's 2035 timeline isn't ambitious, it's a direct challenge. America's 2030 deadline isn't a response. It's a declaration that the United States intends to dominate cislunar space before any competitor even arrives. The race is already underway, and most people don't realize we're in the middle of the most consequential competition since the original space race of the 1960s. So what happens when Draco successfully fires that first nuclear thermal engine in orbit? When NASA's reactors power up on the lunar surface while China is still 5 years away? We'll find out soon enough. If this breakdown of the nuclear space race opened your eyes to what's really happening above our heads, hit that like button and subscribe to New Space Review. Drop a comment telling me whether you think America can actually beat China's timeline, or if we're watching the beginning of a new superpower dominating space. Share this with anyone who still thinks solar panels are the future beyond Earth orbit.